Okay, children, today I am not in class today, as you can tell, but hopefully the sub has managed to click play, or at least one of you has managed to click play and are watching this video. You should have already done your opening activity. It's minute math, so it takes 1 minute, maybe 2 minutes, because you have 1 minute to do it, and then 1 minute to email it to me. And I'm checking my email as we speak to make sure that you guys have sent me that kind of stuff. So, moving on from that, that should be done. Now you guys have a video to watch. You don't need your iPads for this unless you really want to take notes, and the sub's going to be watching and making sure that you are actually taking notes on something like Notability or GoodNote or just the little Note or Pages app. But you're not to be multitasking and going on Hipstagram, Twitter, Snapchat, whatever. Unless you have questions about something, which will come later. Okay? So please make sure you're paying attention to this video. Unfortunately, there's no actual video of me because, you know, right when I needed it to work, it didn't work. So that's just how technology works. So you get my voice, my lovely voice, and some videos that I put together here, and some discussion. First, I'm going to show you guys a little intro Global Warming 101 kind of video from National Geographic to give you guys a little bit of information, which is some stuff you should already have from the Intro to Natural Resources thing that we did and from the Energy Sources thing. So, enjoy.
For 2.5 million years, the Earth's climate has fluctuated, cycling from ice ages to warmer periods. But in the last century, the planet's temperature has risen unusually fast, about 1.2 to 1.4 degrees Fahrenheit. Scientists believe it's human activity that's driving the temperatures up, a process known as global warming. Ever since the Industrial Revolution began, factories, power plants, and eventually cars have burned fossil fuels such as oil and coal, releasing huge amounts of carbon dioxide and other gases into the atmosphere. These greenhouse gases trap heat near the Earth through a naturally occurring process called the greenhouse effect. The greenhouse effect begins with the sun and the energy it radiates to the Earth. The Earth and the atmosphere absorb some of this energy, while the rest is radiated back into space. Naturally occurring gases in the atmosphere trap some of this energy and reflect it back, warming the Earth. Scientists now believe that the greenhouse effect is being intensified by the extra greenhouse gases that humans have released. Evidence for global warming includes a recent string of very warm years. Scientists report that 1998 was the warmest year in measured history, with 2005 coming in second. Meanwhile, readings taken from ice cores show that the greenhouse gases carbon dioxide and methane have hit their highest levels in the past 420,000 years. Arctic sea ice is also shrinking. According to NASA studies, the extent of Arctic sea ice has declined about 10% in the last 30 years. As long as industrialized nations consume energy and developing countries increase their fossil fuel consumption, the concentration of greenhouse gases in the atmosphere will continue to rise. Researchers predict that temperatures will increase about 2 to 10 degrees Fahrenheit by the end of the century. What's less certain is what rising temperatures mean for the planet. Some climate models predict subtle changes. Others forecast rising sea levels which could flood coastal areas around the world. Weather patterns could change, making hurricanes more frequent. Severe droughts could become more common in warm areas, and species unable to adapt to the changing conditions would face extinction. Although much remains to be learned about global warming, many organizations advocate cutting greenhouse gas emissions to reduce the impact of global warming. Consumers can help by saving energy around the house, switching to compact fluorescent light bulbs, and driving fewer miles in the car each week. These simple changes may help keep the Earth cooler in the future.
Back when we started this unit, we looked at energy sources from the U.S., primary energy consumption in terms of percent in 1973 and in 1997. I wanted to think about and look at question number 4 from that, which asked which source increased the most from 1973 to 1997, and why do you think that is? A lot of you said that the source that increased the most was coal, going from 17.5% to 53%, which to me is really only an increase of about, a little more than doubling, versus nuclear power, which went from 1% to 18% of our energy consumption. So I wanted to just point that out to you guys and ask you rhetorically, which means you don't actually have to answer out loud. You can email me if you want. But why do you think that is? Why do you think I would point out the difference between coal increasing only twofold and nuclear power really increasing almost 15-fold? The other thing I really want you guys to get out of this data is from question 7, which asks how global warming provides evidence for the amount of energy use that changed from 1973 to 1997. So what that's asking is, how does global warming provide evidence of the change in energy consumption? Did you guys think that, excuse me, did you think that energy went up, stayed the same, or went down? So, if global warming is caused by greenhouse gases going into the atmosphere, and greenhouse gases are caused by burning of fossil fuels and other industrialization, then my logical assumption would be that energy consumption from 73 to 97 to now, it's gone up. And the other thing that you could logically assume, 2 other things from 1973 to 1997. One, the population has definitely increased. We have over 7 billion people on the planet today in 2013. In November, we actually reached the 7 billion mark, which we did not have 7 billion people back in 1973. So if we have 7 billion people that need energy and need electricity and all that, then we are burning a lot more fossil fuels and consuming a lot more energy. And the other thing is technology has increased. So if the technology to burn fossil fuels and the technology to produce and consume energy has gone up, then the energy that we consume in actuality is going to go up as well. Not just changing what type of energy we use, but the fact that we're going to use more of it because we have more technology and higher levels of need for that technology, so we're going to plug in more of our computers and iPads and all that, so we're going to consume more energy in the process. Earth's natural resources are divided into 2 categories, non-renewable and renewable. Renewable resources are usually living and therefore can renew themselves, assuming they are not over-harvested, such as trees, crops, livestock, or fish. Flow resources are a form of renewable resource, but they don't need regeneration or regrowth like trees or fish. So this would be something like geothermal, solar power, wind, tides, waterfalls, things like that. Non-renewable resources are those that cannot be replaced once they've been consumed or harvested. They include fossil fuels like oil or petroleum, natural gas, coal, and uranium. I wanted to take a second to talk to you guys about the greenhouse effect. I think it's something you guys have probably heard as you're growing up in terms of the greenhouse effect is what's causing global warming, yada yada, but it's actually, as you might have gotten from the other video you watched and from the web quest you did, it's actually really beneficial to us and animals and plants that live on Earth, because without it, the Earth would be inhospitable. It would be as cold as the moon, the dark side of the moon, or the light side of the moon. I mean, if the sun's energy wasn't able to be trapped within the Earth's atmosphere and warm the plants and animals and water that are here, then we wouldn't be able to survive. So just quickly, I wanted to point out the sun's energy, the light waves come down into the Earth and break through the atmosphere and warm the land and sea. Okay, some of that energy is radiated back out and leaves the atmosphere, goes back into space as infrared waves. So this is radiation. Okay, so once the Earth, the land, and sea has heated up, the energy that leaves is now radiation. It's not reflection. It's not the sun's light bouncing off the Earth and bouncing back. It's the energy has changed to radiation. Okay? Some of that radiant energy gets trapped because it bounces off greenhouse gases that are naturally found in the atmosphere, such as nitrous oxide, carbon dioxide, methane, water vapor, and of course fluorinated gases, which aren't there naturally. But there are 4 greenhouse gases that are there naturally that help to trap radiant energy and cycle it back and forth to keep it inside the Earth's atmosphere, and to keep us warm and to keep us at a nice livable temperature that we've gotten used to over the past million or so years. Really over the past like millions and billions of years, but you know, a day, whatever, no big deal. Each greenhouse gas actually naturally gets into the atmosphere in different ways. Carbon dioxide is produced from humans and animals breathing. That's one way that carbon dioxide gets into the atmosphere. Methane is a natural thing that is produced by some bacteria. It's also produced by cows and other livestock and humans when they flatulate. That is the scientific and appropriate term for where methane comes from. It also comes from burping and really just from livestock breathing. CFCs are not a natural, not really all that natural in terms of greenhouse gases. They're used in coolants and air conditioners and things like that, and they're also used in pressurized cans like hairspray. I would say 10 or 20, 30 years ago, they were used in hairspray and other things like that to produce pressurized nozzles so that stuff would spray out really quickly. But those CFCs get up into the atmosphere and react with ozone, which is O3, and break down ozone, which is, you know, a long time ago to you guys, is what was causing a hole in the ozone layer and depleting the ozone layer. So we have, as a nation and as the Earth and the world, we've decided that maybe we shouldn't be using those. We should come up with different ways to cool things and to pressurize stuff, because that's really seriously depleting the ozone and causing the greenhouse gas effect a lot more seriously than carbon dioxide. And nitrous oxide is produced from bacteria. It naturally breaks down bacteria naturally breaks down nitrogen and stuff that's found in plants and in plant roots to nitrous oxide, which is then excised or breathed out by bacteria and enters the atmosphere. It also comes from more unnaturally when we use fertilizer on our plants, like when in corn or soy or other things that we're growing. When we use fertilizer, bacteria break that down too, so they want the nitrogen that's in fertilizer, but if you're putting fertilizer on your plants, you're creating more nitrogen to be broken down into nitrous oxide, which then creates more nitrous oxide in the environment and in the atmosphere. In this video, in this lecture today, I also wanted to take a second to talk to you guys about the signs of climate change. So we're looking at the greenhouse effect and greenhouse gases and seeing that over time, over the past 100 years or so since the Industrial Revolution, greenhouse gases in the atmosphere have increased significantly. They've actually increased, they're higher than they have been in about 420,000 years, as you heard in the video earlier. So what I wanted to do was talk to you guys and look at the different signs of climate change and talk to you about why it matters. I mean, obviously it's like for higher temperatures, for example, for this one here, higher temperatures. It's obvious that higher temperatures are causing more droughts, and higher temperatures can also affect your health, because older people and kids can't handle high temperatures. You can get heat cramps, heat stroke, you can die from higher temperatures, and especially in the US we're seeing that the temperature is really increasing quite a bit. But for me, why it matters is because warmer temperatures will lead to chain reactions of other types of changes around the world. if you increase the air temperature, it changes the oceans, it changes weather patterns, it melts snow and ice, and it changes how plants and animals are able to survive. Because if a plant or animal survives at 20 degrees Celsius and the atmosphere and the air and the land is 21 or 22 degrees Celsius, that's a significant change for that plant or animal. And so some animals and plants could face extinction. For us humans, it's not that big a deal. We just, turn up the thermostat or turn down the thermostat, turn the air conditioner on or a fan, which is really disappointing and sad that it doesn't really matter to us. Anyway, moving on. More droughts means that there's less water available for drinking. That's a really big deal. And you also can't water crops, and you can't make electricity at hydro dams, so you have to rely on other energy sources to provide electricity. Another sign of climate change is the wilder weather that we've been seeing. One of the big things that I've noticed in looking at this kind of data is that the hurricane strength in the North Atlantic Ocean from 1950 to 2010, there was kind of a dip, but really from 1980 and on, the hurricane strength has really significantly increased in terms of the power dissipation index, which is a really fancy way to measure the strength of a hurricane. And if that wilder weather is happening, hurricanes cause flooding, damage buildings, roads, structures, things like that, harm crops, and obviously put people's lives in danger, which is, we don't want people dying needlessly because we've changed the climate so much that hurricanes are stronger. And the storms that we see where, like just recently, we had 3 feet of snow dumped on Maine, and the next day it was warm enough for it to rain. I think that's crazy. Which leads me to talk about changing rain and snow patterns, which it doesn't seem like that big a deal, but for places that rely on a specific amount of rain at a specific time of year or depend on snow melt to refill rivers and ponds and lakes, it's a really big deal because you need that for drinking and watering crops and other stuff. So if the climate changes that much that the rain and snow don't happen the same time or as much or as little as they usually do, that really causes a chain effect and a butterfly effect in land and in crop and things like that. Less snowpack is another thing that to me is related to rain and snow patterns and wilder weather. When snowpack melts in the spring and in the summer, it provides fresh water for rivers and streams. So it refreshes it refreshes rivers and ponds and lakes, and so it refills those reservoirs for people who need drinking water, or for cities and towns that need drinking water. It's also important recreationally. It's also important for things like snowboarding and skiing, where I believe last winter, I don't ski or snowboard anymore. I used to snowboard, but I've never skied. I believe last winter we had one snowstorm, and then Sugarloaf and all the other mountains up here had to create fake snow so that people could go snow skiing and go snowboarding, because if there's no weather, if there's no moisture in the air to create snow, and the snow pattern and the snowfall pattern changes, then we're not going to get snow up here, and then we're not going to be able to go snowboarding. I think that's probably the worst sign of climate change that there is, and the worst and most major effect, at least for Maine, is we can't go snowboarding. That's horrific. So a lot of you probably didn't click on this one, the thawing permafrost. So for those of you that don't know, perma would be permanent and frost would be frozen. So in other words, it's a layer of rock or soil that's frozen all year round. So people that build their houses on permafrost depend on that layer of earth staying the same way. So as it thaws, houses will sink and tip down. Even during warmer times of the year, it doesn't unfreeze. So now with global warming and with climate change, the permafrost unfreezing is causing houses to tilt and some pretty crazy stuff to happen. Really? Oh my god, that stinks. Permafrost also has a lot of carbon and methane trapped within it, so as it melts, that's going to be released into the atmosphere and cause more global warming, which is just magical. That it's this little cycle of when one thing happens, it makes something else happen, which makes that one thing happen again, and it just keeps exacerbating the situation. It's so frustrating. It's so frustrating. Okay, so melting glaciers should be obvious because as glaciers melt, it causes the sea level to rise, and as sea level rises, people that live on coastal places are going to be in some serious trouble because the sea level will be higher than it used to be. Same with shrinking sea ice. This is really more of an issue for animals that consider sea ice their home, like polar bears and penguins and things like that. They live on this ice, so if that ice isn't there, they have to spend more of their time in the water, where they will get eaten by orcas. Another sign of climate change that's a really big problem, maybe you guys don't see it that way, but actually over the past 150 years or so, the sea level has risen about 10 inches, 9 or 10 inches in about 150 years. So to me, that's a lot of change. So in another 150 years, when it's gone up another 10 inches, that's a lot of land that no longer is above sea level. Warm oceans really, stupid. Warmer oceans, you might think that because of what I said earlier about higher temperatures that plants and animals can't survive if the temperatures go up too high. So warmer oceans is probably the same thing. Certain plants and animals and ecosystems won't be able to survive because the ocean is warmer than it usually is. But really, on the human level, a warmer ocean affects weather patterns and can cause more powerful tropical storms. So it cycles back to the wilder weather that I was talking about. Like Hurricane Sandy was devastating and didn't happen where hurricanes usually happen. I think it's hard to deny that climate change is happening. It's frustrating that there are people out there still that deny that climate change is happening and deny that it's possibly man-made and human-caused. And lastly, a major sign of climate change is increased ocean acidity. And I'm not sure how much you guys know about acidity, acids, and bases, but CO2, carbon dioxide, is a weak acid. So as there's more CO2 pumped into the environment, you guys might know from the carbon cycle that CO2 is also stored in water, such as the ocean. So if more CO2 is pumped into the environment, including the ocean, that's going to increase the acidity level of the ocean. It's actually from like 1985 to now, in 20 years, it's gone up by about 100, well, maybe closer to like 80 units. That's the partial pressure of dissolved carbon dioxide in the ocean. So if the ocean's acidity increases, that's it. One of the things that upsets me the most is like coral reefs can't build their skeletons correctly because they need a certain acidity level in the ocean to be able to build their skeletons. And same for other shellfish like lobster, which is our livelihood. So if lobster can't build their shells, can't grow correctly because they're not under the right acidity level, because the ocean's too acidic, it's not basic enough, then we all of a sudden don't have lobsters to export to all of these countries and cities and towns and places outside of Maine that love their lobster. It's like, that's just on a small Maine scale. Yeah. I don't know if you guys can tell, but climate change really ticks me off. Okay, I just took a minute to calm down a little. I want to talk about fossil fuels, which are kind of a huge reason for this ever-increasing and more rapid climate change that we're experiencing. I'm clearly still a little upset about it, but it's okay. Fossil fuels there are three: coal, oil, and natural gas. A lot of you on that WebQuest saw that there were 4 things listed under non-renewable resources, and that includes uranium. But uranium is not a fossil fuel, and that's because of how fossil fuels are made. Okay, I have a picture up here of the carbon cycle to give you guys an idea of how carbon naturally exists in the earth. So I'll just bring my little call out here. Plant respiration produces oxygen, which we breathe in, and then we breathe out carbon dioxide. Okay, then plants take that carbon dioxide back in to produce sugars that we then eat. So we have sugars and carbon in us, and plants have sugars and carbon in them, and there's also carbon dioxide in the atmosphere. So carbon exists really everywhere on the earth. When these organisms decay, when they die, when plants and animals die and decay, they gradually sink down under layers of dirt and sediment, and eventually, when they're under enough layers, they become fossils. And when they're under enough layers, there's a lot of heat because they're getting closer to the mantle, and that heat comes from the sun's energy, of course. But that heat and that pressure, the more layers that they're under, causes more pressure. And so that combination of heat and pressure, you guys might know that heat and pressure causes coal to eventually become diamond. But before these fossils and these dead organisms become coal and then become diamond, the heat and pressure causes them to decay only partially, and so that carbon either becomes petroleum, which is oil, and so it decays to that point. And it all depends on where it's happening, whether or not it becomes natural gas, which is carbon dioxide and methane, or whether it becomes coal and it's like really solid, or whether it becomes oil and it's a liquid. So because of that, that's why uranium is not a fossil fuel, simply because it's not made from fossils. Here's a look at some technologies that shift the energy demand from fossil fuels to any number of clean energy sources. Be a part of the solution. You children, please do it. One of these days, one of you, you're 14. 14 years from now, when you're out of high school and out of your master's degree or PhD, you will have come up with the electric car, or a car that doesn't need to be charged with its electric battery, or an electric battery that's safe to dispose of in landfills, and you're going to be bajillionaires. So start thinking about it now.
Hi, I'm Ron Kogan with greencar.com. Today we're going to talk about how hybrid cars work, like this Nissan Altima hybrid I'm standing in front of. Regular cars use an internal combustion engine. It usually runs on gasoline, some run on diesel. Those are the two choices. Today we have hybrid electric cars. Those combine standard internal combustion drive along with an electric motor powered by batteries. Hybrid cars are very efficient by nature. Most of them are designed so that when you're first starting out, you're driving on electric power. As the car picks up speed, the internal combustion engine takes over seamlessly. You can't even feel it. And you drive along that way. If you need more power as you're passing or climbing a hill, the electric motor joins in, gives you even more power to do those very efficiently. The advantage of a hybrid car is the very fact that it has those two power sources. Electric motors are inherently very efficient. The problem is you can't drive on electric power for great distances or at great speeds because it takes a lot of battery power. Batteries are expensive, they're heavy, and you have to put a lot of them in a car to be able to work on electricity only. That's being worked on with electric cars, and we'll see that coming in the years ahead. Today, hybrids have an advantage because they have those two power sources. They'll use the appropriate power source when it's needed under specific conditions. And in the end, you get extremely high fuel efficiency, up to 45, 50 miles per gallon in some instances, and extremely low emissions, which is important for the air quality in our cities today. Hi, I'm Ron Kogan with greencar.com. Today we're going to talk about the pros and cons of hybrid vehicles. First of all, let's talk about the pros. Extremely low emissions, very high fuel efficiency compared to most vehicles. What's not to like? Depending on the hybrid model you choose, that fuel efficiency could be up to 50 miles per gallon or more. So hybrids certainly have a place on the road today. Now, when people start talking about the cons of hybrids, they're really thinking about two things, and that would be the cost. Typically, hybrids are going to cost anywhere from $1,500 to maybe $3,000 or $4,000 more, depending. Mild hybrids, the ones that just give you a slight bump in fuel economy, are the ones that will come in about $1,500. Full hybrids, more likely $3,000 or so. The other con that people talk about involves the batteries. There are two issues here. First of all, how long are the batteries going to last? And really nobody knows, because hybrids haven't been out long enough to be able to prove that in the real world. A lot of bench testing has been done, a lot of laboratory testing. Automakers already warranty them for 8 to 10 years, say they'll last the life of the car, but eventually those batteries will need to be replaced. Another issue with batteries is what happens to them in the end. Where do they go? Is it a problem for our landfills? And the answer is no. It's not a problem. Their batteries are already cycled. It's one of the great success stories. A lot of batteries are diverted from landfills. Companies have very dynamic programs for turning in old batteries so they can be dealt with properly and recycled. It's also a very highly regulated industry. Nickel metal hydride batteries are the type that are in hybrid cars. Same story. And when we get beyond that into electric cars with perhaps other battery technologies, it will be the same as well. Batteries will be recycled. They'll stay out of the landfill.
Chevron is very interested in the climate change issue because it is an important issue. It has to do with the kind of energy and the fuels that we produce that the world needs.
Climate change is undoubtedly the greatest environmental threat that humanity has to face in the next 100 years. Chevron has been an early and strong supporter of the program that we've developed at MIT that integrates the science, the economics, the technology, and the policy of this issue in ways that we hope will be exceedingly important in providing advice to policymakers going into the future.
The biggest challenge about climate change is that there is no one single answer, no one single solution. We really need to develop a whole host of technologies and also continue to improve our energy efficiency, continue to do that, but at the same time develop new technologies. Now, one of the new technologies that we've been looking to develop and deploy is CO2 capture and storage. Carbon capture and storage is all about capturing the carbon dioxide or CO2 that comes from power generation, or from our industry, from refineries, for example, and also from natural gas production. First, the CO2 is separated, and the captured CO2 is compressed to a density that's very similar to a light liquid. Now, after compression, the CO2 is injected into suitable reservoirs beneath the earth. So what this means is that safely storing CO2 underground will help reduce greenhouse gas emissions that come from energy production. Climate change is a very important issue. It's also a very complicated one. There's so many aspects to it that's challenging to me, and I wouldn't be doing this job if it weren't challenging.
There's no fear of the dark at this farm in eastern Ontario. That's thanks to power generated through the production and processing of methane gas. And there's a steady supply.
We knew how much energy is in manure from past experience. We tried a bit in Switzerland to make heat out of methane gas. There is about 1.5 to 2.5 kilowatt hours per cow per day in well-fed dairy cows. So our consumer day is about 450 kilowatt hours, and with our animals about 250 animals, large animals, times 2 kilowatt hours would be about 400 kilowatt hours. So we figured that we would be able to produce our power if the system would run well.
Paul and Fritz Clazy arrived in Canada in 1990, armed with the desire to be dairy farmers and to apply their technical knowledge to explore green energy. The Clazy brothers milk 140 head of cows and have 280 head of livestock. 6,000 cubic meters a year of manure is produced.
The manure comes out from the cow, goes into the gutter. We run the gutter twice a day, morning and night. The manure goes all around behind the cows and comes up here. This incline goes down in a 3-foot pipe. It's no pump, it's gravity fed and runs out to the digester.
The manure is stored for 28 days in the digester. Helpful bacteria naturally present get the process going until the manure is well fermented. Heat is essential to this whole process, especially given cool Canadian winters. The manure has to be kept at around 40 degrees Celsius to have perfect fermentation.
So what we did here on this farm, we tried to build a heat exchanger where we can exchange the warm manure who goes out from the digester with the cold manure who comes in from the barn. What we also do, we use from the milk cooling, we make hot water from the milk that we cool down. We have to cool the milk from 36 degrees down to about 2 to 3 degrees.
The fermentation process produces methane, nutrient-rich manure, and ammonia. Manure is comprised of between 40 and 60% methane, compared to natural gas, which has a methane content closer to 90%.
Rubber-sized tarp on top of that works as a storage for our gas. So this bubble is like a balloon, goes up and down. We have a storage room from about 150 cubic meters of gas, if it's full or empty.
A full dome represents 250 kilowatt hours of power, which occurs twice a day, every day.
Manure is considered to be liquid gold by farmers, and that's doubly true for the Clazy brothers. As this dome drops, energy is directed to the Hydro One power grid, forcing their electricity bill down.
The valve has opened now, and here we lose now methane gas because the balloon is full, and we really should start up the generator. Here the methane gas comes into the generator. Here we measure the volume of the gas with a meter, and then we go in up here to the turbocharger where the gas gets mixed with air. It goes through the aftercooler of the turbocharger and comes in here into the diesel engine. Now the engine started.
This powerful system and some good negotiation has resulted in a net metering agreement with Hydro One for the Clazys. They feed the province's power grid when the generator runs and the farm's not using the energy produced. And here's something you don't see often, a hydrometer running backwards. Paul Clazy sees many pluses to the process.
One advantage is usage of the power. Another advantage which we really like is that during the summertime we can make the hot water in the houses, and we think largely we can probably heat the houses with the energy the heat which comes out of the generator. And a big part of all is the digestion of the manure, which really we like to see that the manure is much more available to the plants, and all the bacteria which E. coli and so on are gone in the manure. Yeah.
The sustained heat also kills weed seeds, a big advantage for any farmer, reducing requirements for spraying. So it's value added to value.
We are a bit pioneers, I would say. We imported a lot of stuff from Europe. And we put the system together here ourselves. We have some technical knowledge.
Paul has been able to put his experience as an inspector for Hydro Zurich to good use, combined with Fritz's dairy farmer background, as they examine records of energy produced on site since the system's installation. They have reason to smile.
It looks good, but we have also other considerations. We spent some money on the system. We knew that the system will work. We're not exactly sure if we can come to a level of zero, but I think we will come very close to it. Yeah.
The units for greenhouse gas emissions are tons of carbon dioxide equivalent per year. The reason they lump it all into one greenhouse gas, just carbon dioxide, is because it's really difficult to factor in how methane affects it, how nitrous oxide affects it, etc., etc. Methane is more powerful a greenhouse gas than carbon dioxide, just like CFCs and water vapor are more powerful, or at least affect carbon dioxide warming a lot more. So the equivalent piece is that we're just kind of calling all greenhouse gases carbon dioxide and leveling them to the point that the tonnage of carbon dioxide that you put out is not just carbon dioxide, but it's the carbon dioxide equivalent.
Hello, my name is Hank Green. I'm the chief editor of EcoGeek.org, and today I am bringing you light bulbs. Light bulbs. I've been getting all these light bulbs for sample posts, and now I have enough that I can actually do a comparison between CFLs and LEDs and regular incandescents and other LEDs. That's what we're going to do today, beginning with your traditional incandescent light bulb. Here we have a 40-watt incandescent light bulb pulling 38 watts. As to be expected. I can already feel this getting quite hot in my hand. It's a little space heater. If you're ever cold, you just put one of them in your shirt pocket and it will burn your shirt. This is a 40-watt rated CFL. They look pretty much exactly the same, except this one is a little bit brighter. And maybe the light is a little bit warmer coming off of this thing than this thing. This was at 39 watts. This is pulling 14. So yes, CFLs are better for you and for the environment. Hooray! Ow! I know what you're thinking. You're the chief editor of EcoGeek. Why do you have an incandescent light bulb in your house? Well, I went out and bought one so that I could do this test, okay? And I'm never gonna use it again. So that was very efficient of me. Now we have a very exciting light bulb. This is the EarthLED CL3. It's one of the most compact, most efficient, and best LED light bulbs out there from EarthLED, one of the greatest companies currently making these things right now. This is a 20-watt equivalent, so this isn't going to be exactly the same, as you can tell. So this guy right now, I told you before, pulling about 14 watts. 3. Between 2 and 3. Is how much this is pulling. So that's just amazing. Obviously, one of the big problems with LED light bulbs is that they're not always quite as bright as you would like them to be. And they have to stay cool. So when you start making LED light bulbs that are really bright, they get too hot and their life is decreased. And one of the greatest things about this guy is that it probably is still going to be working when I'm like 50 or 60 years old. I also have for you the cheapest LED option that you can possibly find. I bought this, the Decor LED Accent, at Ace Hardware for $9.99. It is actually just a bunch of LEDs stacked together like you would find in normal equipment. They're high brightness, of course, but they're the same technology, basically. No crap is pulling off of my kilowatt 0 watts, which means less than 0.5 watts is how much this is eating up right now. It's not very bright, the equivalent of a 10-watt incandescent light bulb, but it's pretty fantastic for the price if you want to put it in a closet or somewhere where you're not going to use it a lot, because CFLs don't like to be turned on and off a lot. Obviously not a 40-watt equivalent. Heat-free technology, lights up faster. You'll never change your bulbs again. I don't know what they're basing that on. statement based on the minimum number of times the LED bulb needs to be changed. Whatever. Not very honest. This is the Earth-led Zetolux warm white bulb. You will see that this is a little bit warmer than this. But the light quality coming off of here is, as you can see, pretty warm. I'm not turning into a pasty white cubicle drone or anything. So this actually uses cooling elements all along the outside, and that keeps the LED cool. This 40 watt equivalent bulb, right now pulling 5 watts. This, again, like 15. This is 3 times more efficient than a CFL. Oh my god, that's so cool. This bad boy is a $50 light bulb, but it's worth every penny because it will last pretty much forever, is 3 times more efficient than a CFL, and the ladies love it. They're totally cool to the touch. Finally, we have the most expensive light bulb I have ever touched in my life. It is the $79.99 Evolux S. This is a warm light bulb. I think it's a 60 or 70 watt equivalent. I can't look at it without hurting my eyes. And because it is producing so much light, the people at Earthlit actually had to figure out a way to keep it cool enough that it wouldn't overheat and decrease the lifespan, which is over 50,000 hours. The way that they've done that is they've actually put a little bitty tiny fan in here, which I don't know if you can hear. There's a tiny fan in here that's basically a processor fan like you would have on your CPU that keeps the LED chip cool so that it doesn't overheat and it will continue to last forever. Because it's using that fan and because it is such a bright bulb, it uses significantly more energy than the Zetolux, but still significantly less energy than the CFL! This is a 10 watt bulb! Oh my god, that's so cool! It is so
It's time to confront a major threat to our global environment. Cows. Yep. Turns out that worldwide, livestock are a major contributor to greenhouse gas pollution, right up there with cars, planes, and trains. And at the rate we're producing beef worldwide, emissions from cows, along with other harmful practices in beef production, threaten to mess up our climate, land, and water. Big time. On average, Americans eat 3 times more meat than people in other countries. From the end of World War II to the mid-1970s, beef consumption per person doubled. The U.S. is now the largest beef producer in the world. Our beef industry is a powerhouse worth $74 billion a year and providing millions of jobs. Today, more and more Americans are choosing chicken and pork, even tofu. But much of the meat we eat is still beef. Let's look at an all-American food, the hamburger. On average, we eat about 3 burgers per week. So let's see. If all 313 million Americans eat 3 burgers per week, that's 156 burgers per person per year. Altogether, that's more than 48 billion burgers every year. A quarter pounder at a fast food joint costs about $3 or $4. That's pretty cheap. But what we don't pay for at the counter, we end up paying for in other ways. What are the hidden costs? First of all, cows take up a lot of space. Worldwide, livestock use 30% of the Earth's entire land area. That's counting pastures and land used to grow grain for feed. We use about 8 times as much land for feeding animals as for feeding humans. And in places like Brazil, acres of forest are still being cleared for livestock, which creates pollution and also removes a perfect sponge for absorbing carbon dioxide. And did someone mention water? It takes about 1,800 gallons of water to make a single pound of grain-fed beef. That's about 4 times the amount for chicken and more than 10 times the amount for a pound of wheat. Why does it take so much land and water to feed cows? Well, for one thing, cows eat a lot. During the first 6 months, a calf eats and eats and eats. When it's about 700 pounds, it's sold at auction, usually to a feedlot, which is like a very crowded cow city. At the feedlot, the cow continues to eat and eat and eat. At most feedlots, cows eat a mixture of soy and corn. This whole feed system's pretty new. Before the 1970s, cows ate mostly grass. Then Congress passed a farm bill that changed everything. The government started paying farmers to grow feed crops like corn and soy. It also helped pay for more fertilizer. So, voila, now corn is in everything from sodas to cereal. And most of the country's 90 million cows now get corn for breakfast, lunch, and dinner. Unfortunately, cows are built to digest grass. Corn can make them bloat with gas, and cows make a lot of gas. This is no joke. See, cows are ruminants, meaning they create methane gas when they digest food. Chickens and pigs don't. Methane has 21 times more climate-changing power than CO2. In America, cows produce more greenhouse gas than 22 million cars per year. America's cows create about 500 million tons of manure in a year. That's 3 times as much as we humans do. Cow manure also creates nitrous oxide, which has 300 times the global warming effect of CO2. Cow manure is responsible for 2/3 of all the nitrous oxide pollution in the world. There's another source of nitrous oxide in a cow's life cycle: fertilizer. We Americans use about 17 billion pounds of nitrogen fertilizer to grow feed for our cows. When runoff from fertilizer and manure flow into rivers and then to the ocean, they create huge algae blooms, which suck the oxygen out of the water and leave dead zones where no life can survive. Anyway, back to the feedlot. Once the cows are fattened up, they head to the slaughterhouse. Slaughterhouses create about 30 million pounds of contaminants a year, mainly nitrates and ammonia used to disinfect meat. From the slaughterhouse, the beef is shipped to big processing centers where California beef is mixed with Texas beef and Colorado beef. One burger patty can contain the DNA of more than 1,000 cows. That means a single case of E. coli could easily spread to thousands of burgers. Trucking all that beef around creates pollution too. This isn't an exact science, and the numbers vary depending on how the cows were raised. But a single quarter pounder clocks in at about 6.5 pounds of greenhouse gases. That might not sound like much, but with Americans eating 3 burgers per week, that's more than 158 million tons of greenhouse gases per year, about the same amount as 34 coal-fired power plants. It's not the cow's fault. It's the system we've created to mass-produce beef that's the problem. Too many burgers take a toll on the environment. They can take a toll on your body, too. This is the recommended daily diet. And this is how most Americans actually eat. We eat too much meat, grains, fat, and sugar, and not enough fruits and vegetables. Many studies show that eating too much red meat can lead to heart disease, high blood pressure, and even diabetes. The hidden costs add up. One research group figured the cost just in greenhouse gases, water for growing cattle feed, and healthcare at about $1.51 for every burger. Multiply that by the 48 billion burgers Americans eat every year, and that's more than $72 billion. We don't pay for it at the store or at the fast food joint, but we pay for it in other ways. So what can we do? Well, we don't have to give up meat to change our impact. Cutting out just 1 burger per week would remove as much greenhouse gas pollution as taking your car off the road for 350 miles. If all Americans ate no meat or cheese 1 day a week, it would have the same climate change prevention effect as taking 7.6 million cars off the road for 1 year. And while it's more expensive, grass-fed beef does less damage to the environment. Even the smallest choices make a big difference to the environment, to our neighbors, to our health. In the US, people are starting to eat less meat, but the rest of the world is eating more. Just imagine, what if all 1.3 billion people in China ate 3 burgers a week, like we do? Could our planet keep up?
Well, good afternoon. It is time for your Farm and Ranch News. With me today, Dr. Jude Capper, now with Washington State University formerly, but you now just moved on to a new part of your career. Tell me what you're up to, Jude.
I'm consulting and doing some research with the beef industry, mainly looking at carbon footprint, land use and water use, and the improvements we made over time.
All right. Well, Dr. Capper, as we talk about the carbon footprint of beef, I think that there are a lot of common misconceptions out there. And you told me we've made a lot of strides since our fathers and our grandfathers' generations. What have we done?
The beef industry has done some great stuff. We've improved productivity, animal welfare, nutrition, management. We know far better now how to care for all of our cows, and that's improved weight at harvest, that's improved growth rate, and so that's cut our carbon footprint across the board.
And you know, you're based in science, and we tend to all be based in science and agriculture, and it's great to have you doing this research and really having that information out there for folks with the beef checkoff or with anything else. What are some of the numbers that you can give us about how we've improved our carbon footprint?
Sure. So compared to 1977, for example, a pound of beef now has a carbon footprint that's 16% lower. We use 12% less water per pound of beef, we use 9% less fossil fuels per pound of beef, and we use 33% less land, and that one's really crucial.
And then there's always talk about grass-fed beef versus beef that's in the feedlot, and you said there's also differences in those carbon footprints.
Absolutely. There's a place for every system, whether it's local, organic, corn-fed, grass-fed, whatever it could be. But if we generally moved to a less productive type system, then we do use actually more carbon, more land, more water per pound of beef in a grass-fed type system than a corn-fed system.
Well, you've been taking a tour around Montana. You're here for a week long. I know Lauren Chase with the Montana Stock Growers has been your fearless escort, taking pictures along the way, but you're looking at beef production here in Montana and across our region. What have you seen?
Oh, it's been the best trip I've ever had. It's been fabulous. Beautiful cows, beautiful calves, mountains, the best ranches I've ever seen. It's just blown me away. It's been fabulous.
All right. Thank you so much again. That is Dr. Jude Capper, formerly with Washington State University. Thanks for being with us.
Thank you.
Absolutely. And to get more from her, just visit our website at northernag.net. Stay with us. The markets are next.
EcoMaine is a nonprofit organization owned and operated by 21 municipalities, which provides environmentally sound disposal services to a total of more than 40 communities. We advocate the state of Maine's waste disposal hierarchy, which, in order of preference, is to reduce, reuse, recycle, compost, waste to energy, and lastly, landfill. EcoMaine is one organization with 3 disposal facilities: our single-sort recycling system, our waste-to-energy plant, and our state-of-the-art landfill. Single-sort recycling means that you only need to separate recyclables from trash. All recyclable paper, glass, cardboard, metal, and plastic are thrown together in just one container, where it is picked up by your contracted hauler or municipality and brought to our facility. There it is weighed at our scale house and delivered to our tipping floor. There, a front-end loader puts the material onto a conveyor to begin the process of separating the mixed material into 10 separate types. There are many steps in this process which must be done before materials can be sold for reuse in manufacturing. One of the first steps separates newspaper. All material on the conveyor is dropped onto spinning star-shaped cogs. These cogs are placed in a specific configuration that causes the large pieces of newspaper to ride over the top while smaller materials fall between them. The newspaper travels onto a storage bin while all the remaining materials continue on to the next step. The process continues with various other methods of separating out materials. For example, magnets pick out the ferrous metals. Aluminum is caught using a reverse eddy current. Number 1 plastics are separated using an optical scanner. Glass is ground into very small pieces and stored in piles. At 3 different points in the process, manual sorting helps to catch materials that the automated equipment misses. The process cycle, which separates mixed recyclables into 10 separate categories, takes just 3 minutes to complete. Each type of material is then baled and sold for reuse in manufacturing of new products. The revenue from these sales helps to cover the costs of EcoMaine's 3 operations. So the value of these materials stays high and keeps your cost for waste disposal low. It's important to buy products made from recycled materials. As you can see, recycling greatly reduces waste, but EcoMaine even has a purpose for waste that arrives as trash. EcoMaine uses trash as fuel in its waste-to-energy plant to make electricity. This plant is next door to the recycling facility, where it too has a tipping hall. It receives 160,000 to 170,000 tons of waste each year. The waste goes into a 7-story storage bunker, where a large mechanical claw mixes the waste for a better burn, then picks up as much as 2 tons of waste at a time to feed twin boilers. The boilers burn trash at about 2,000 degrees Fahrenheit 24 hours a day. Gas emissions from the boiler go through several pollution control systems, first to remove nitrogen oxide, then mercury and dioxin, next acid gas, and finally particulate removal. The remaining gas goes through pollution control tests and leaves the stack as water vapor. The walls inside each boiler are lined with 12 miles of water-filled tubes holding 15,000 gallons of water. The intense heat from burning trash turns the water to steam, which is directed to turbine generators to create electricity. EcoMaine produces on average 99,000 megawatt hours of electricity every year, enough to power more than 10,000 homes. About 15% of that power is used to operate the recycling and waste-to-energy facilities, and the remaining 85% is sold. Revenue from the sale of electricity helps to cover part of EcoMaine's costs. In addition to creating electricity, burning reduces waste to just 1/10 its original size. The resulting ash is carried by conveyor belt, and any remaining metal, which is removed by a magnet, is set aside for recycling. The ash continues on into a waiting truck that then delivers it to EcoMaine's landfill just 3 miles away. If instead of trash, unburned trash was taken to the landfill space would need to be 10 times as large. Many environmental safeguards exist for the old landfill section that is now closed. For example, EcoMaine has 2 extensive underground piping systems, one to collect gas created by old decomposing organic material, and another to collect contaminated water. The water, leachate, is pumped to a containment pond, where it then goes to the Portland Waste Treatment System. The water pumping station moves on average 1,600 gallons a day from the 44 acres of closed landfill. Aside from water collected by pipes, cleaner subsurface water is diverted to EcoMaine's wetlands treatment system, a marsh area that cleans the water by natural means. The cattails and reeds extract heavy metals such as arsenic and lead. Blue-green algae on the surface feeds on phosphorus. The red scum layer is created by a bacteria that feeds on iron. Methane gas created by the unburned decomposing organic waste in the closed portion of the landfill is carried by underground pipes to be flared off or used as clean energy. EcoMaine's active ash fill area was constructed in 2006 with $6.8 million in environmental protection technology. Because the landfill ash fill sits atop wet marine clay, EcoMaine has installed geological monitoring equipment to measure any ground movement caused by the weight of its disposed material. At times, EcoMaine temporarily stores unburned trash at the landfill as backup fuel supply for the waste-to-energy plant to ensure the continuous production of electricity. Metal that is extracted from ash at the waste-to-energy plant is also stored at the landfill until it is sold to recyclers. Because of its extensive environmentally sensitive processes, EcoMaine is proud to have earned the International Standards Organization 14001 Certificate for Excellence in Environmental Management. These rigorous standards have been met by the Recycling Center, Waste-to-Energy Plant, and Landfill Ashfill Facility, a rare accomplishment. As you can see, EcoMaine's owner municipalities are dedicated to recycling, to environmental protection, to efficient management of waste disposal costs, and to helping our world stay green.
Synthetic meat. Synthetic meat is made from real animal muscle cells grown by artificial means in the laboratory. Because meat is animal muscle, we can take a small sample of these muscle cells from a living animal and then using a technique called tissue culture, grow enough cells together to make a cut of meat. This meat can then be packaged, sold and eaten, just like normal meat, with the ethical advantage that no animal was harmed in its production. We asked people, what excites you, what frightens you, and how will it change the way you live? These were some of their responses.
Eating is more than just flavour and texture, it's the whole experience. How can technology simulate that?
That's a very good question, especially if you've ever tried textured soy proteins as a meat substitute. But while meat grown in the laboratory is synthetic in its production, it is not artificial. It is still made from exactly the same sorts of muscle cells found in the animal. However, whether it tastes exactly the same or provides the same culinary experience is up to the person eating it.
People are already suspicious of the marketing industry telling us what we should eat. How would synthetic meat be labelled and promoted?
Synthetic meat may well be marketed as the ethical choice. It can be produced without having to kill animals for their meat and potentially has a whole range of additional advantages. Synthetic meat can be grown and its nutritional content optimised to make it healthier by design. It may also help reduce the current carbon footprint associated with meat production. And if synthetic meat really lives up to this potential, it would be likely that labelling and promotion would reflect these benefits.
What chance does synthetic meat have of being a successful alternative?
While synthetic meat exists, it's not possible to produce commercial amounts of it at the moment due to cost. If it were cost competitive and provided the ethical and nutritional advantages it promises, then it probably could be successful. What do you think? Would you eat it?